Example here. Here we have the impulse response, the exponential function, exponential decaying function, and xt is a ramp function at 3 times the ramping rate, and find the yt using convolution integral and also verify with the Laplace transform. Let's first do the convolution integral here, and yt based on the kind of the form we prefer, that goes from 0 to t, ht minus tau, and x tau d tau, right? We can just need to substitute this the expression for ht and the xt. So we replace t by t minus tau for ht. So that goes 0 to t, and 5 times e2 minus 10 times the t. We replace that t by t minus tau, and ut and ut minus tau, and times x tau. X tau is 3 times tau u tau, and we integrate with respect to tau. So in this case, first thing we recognize this is going to be equal to 1 when tau is between 0 and t, because the t minus tau going to be positive, right? So that's 0 and 1, and also for u tau also equal to 1. So therefore we can just drop these two terms, and also I multiply 3 and 5, we get a 15. So I combine 2 steps and drop these two and multiply 3 times the 5 and move it outside this integral. And e2 minus 10 t minus tau times 3 times tau d tau. So in this case, the first one we actually can rewrite the first term 0 to t. The exponential function we can write in that as we can multiply this out, e2 minus 10t times e2 plus 10 tau, right? Times tau d tau, and recognize this t is different from tau, right? So we can move this term outside because this has nothing to do with tau. So therefore I have 15 times e2 minus 10t moving outside, and so we have e2 10 tau, and here this is positive because I had negative sign here and negative sign in front of tau, right? So 2 negative, that become positive, times tau d tau. So what I will do is use the fact that d e2 ax is equal dx is equal a times e2 ax, right? So therefore what I have here is I have dAx would be equal ax a times dx. So I'm trying to get this term to, so in this one here I have e2 ax, right? So what I do here is this one here would be equal to, so therefore I have e to ax times 1 over a, that's going to be equal e to ax dx. So I can change this term and combine these two terms, utilize these with a equal to 10 and x equal to tau. So I can write this term as this 10t 0 to t, and I combine that from the 1 to 10 times tau and de to 10 tau, right? And in this case we are gonna do the based on the chain rule or integration by parts. We have dxy is equal x, let's do x dy x dy is equal dxy minus y dx, right? So in this case, we are recognizing this as tau. So this is the x, yeah, this is the y. So I have x dy. So that the dxy, let's do in, so that 1 over 10, I can move that out. So that become 15 over 10, which is 1.5 times e2 minus 10t. And now I'm having this term. So this term is going to be x times y. So x times y, which is tau times e2 10 tau. Now I need to evaluate tau at the upper and lower limit, not t. The lower limit is 0 and the upper limit is t. Right? So this is the xy term, and minus the second term. The second term is going to be 0 to t and y dx. Y is e2 10 tau and d and dx d tau. Right? So this is this step, and the next step I want to evaluate the first integral here, the first upper lower limit. So the lower limit is tau 0, so that will be 0. So I have t times e2 10t minus 0 for this term. So therefore I got a 1.5 e2 minus 10t, and the first term I left with is t times e2 10t minus 0. And the second term here is I'm gonna use the same thing we had before, right? So the e2 ax dx is equal 1 over. So in this case, I'm getting 1 over 10 and e2 10 tau. Now I evaluate that tau at 0 and t, right? So in this case, what's inside the braces here, 1.5 e2 minus 10t times, the first one is t times 10t, and second one here is minus the upper limit. I have 0.1 times e2 10t, maybe right in 2 steps. So that's the upper limit, and minus 0.1 times e2 10 times 0, that's just a 0.1, right? So therefore I have so if I divide it by 10 here and multiply by 10 inside, so multiply that by 10 inside, so I get 0.15. So in that case, I get rid of this 0.1s. So in this case, e2 minus 10t doesn't really change much. T times e2 10t minus e2 10t minus 1, plus 1 actually, because I have 2 negative signs here. So in this case, if I multiply out, I get 0.5 times e2, so this one and the e2 negative 10t and the e2 10t, that becomes 1. So I'm left with t with the first term, and second term I'm left with 1, right, negative 1, and the last term that's plus e2 minus 10t. So this is the result. This is only correct for t greater than 0, right? For t greater than 0. So that's the output, right? So that's the output using we strictly carry out the convolution integral, although we have unnecessary intermediate steps. I hope that will reduce the possibility to confuse some of you. And let's do the Laplace transform. I hope that's a little bit easier. So in that case, the ys is going to be equal hs times xs. And the hs is equal to the Laplace transform of ht. And if you look at ht here is just the e2 is 5 times e2 minus 10t. In this case, we can use the S-domain translation property, right? So in that case, that should be s, the Laplace transform of ut, which is 1 over s, and replace that s by s plus 10, right? So that's the, we got 5, so that's a 5 over s plus 10, and the xs is Laplace transform of xt. Xt is 3 times 3t ut, and in this case, the ramp function, the Laplace transform is 1 over s squared. So 3 times that's equal 3 over s squared, and therefore ys is equal to 5 over s plus 10, and then times s squared and times 3, right? So we get 15 over s squared times s plus 10, and now we need the partial fraction expansion, right? So in this case, we can do in 2 steps, so that we have the complex pole, we have the multiple poles at s equal to 0, right? So at the origin here, so therefore we factor s1 out, so what we are left with 15 over s plus 10 times s. So let's call this as fs. So we're gonna expand that fs using the cover-up method, and that's gonna be equal k1 over s plus k2 over s plus 10. And k1 plus k2 should be equal to 0 based on sum of residues, right? So the k1 should be equal s times fs. We value that at s equal to 0. In that case, we're going to be equal to, so 15 over s plus 10, and we value that s equal to 0, so that's equal 1.5. So k2 should be equal negative 1.5 if we didn't make any mistake here. S times 10 times fs, then we evaluate at the pole here, which is negative 10, so we have 15 over s, we evaluate that negative 10, no surprise, that's negative 1.5, right? So in this case, we have ys is equal 1 over s times 1.5 divided by s plus negative 1.5 minus 1.5 divided by s plus 10. So in this case, we have 1.5 over s squared minus 1.5 over s plus 10 times s. So in this case, this actually we need another partial fraction expansion, right? And in this case, we don't really need to do that the full partial fraction expansion, because originally with this 15 we got 2 residues, now we got 1.5, so the residues will be reduced by 10 times. So therefore I believe I will get 1.5 over s squared minus 0.15 over s, and the minus 0.15 over s plus 10. I just scale the residues we already had by 10 times. I hope that will work. And in this case, I have 1.5 over s squared minus 0.15 over s plus 0.15 over s plus 10. So if I do the inverse Laplace transform yt, is going to be inverse Laplace transform of the ys. The first one here, that 1 over s squared, that should be ramp function, right? So that's 1.5 t times ut. And the second one is 0, 1.5, 0, yeah, so that's 0, 1.5 times, so 0, 1.5 times ut, and the last one here is plus 0.15 times e2 minus 10t ut. So if I factor everything out, I factor 1.5 out, and collect a ut term. So the first one here, I got a 10t minus 1 plus e2 minus 10t ut. The whole thing times ut. If we compare the original one, I think I got a missed error there. This t should have been a 10, right? Because I multiply everything by 10, but not the first term. So here should be 10t, and here should be 10t as well. Okay, so that's the how we carry out the convolution integral, and also how we verified with the Laplace transform. Of course, they should be the same, unless like I did made some error there. I'm gonna see you the explanation of the sort of the graphic interpretation of this convolution integral in the next video clip.